Okay, so this is our last video on matrix transformations for Math 1410 for spring 2017. This is sort of a slightly more advanced topic associated to matrix transformations, something that if you do take Math 3410 you will see a lot of this sort of thing, but it's worth kind of taking a quick look at this because it's something that that kind of, well, one, helps us understand what's going on with some of these examples we've seen. Especially that example we saw where, a transformation of the plane where when we transformed our little square, we didn't get a parallelogram, we just got a line. So what's going on there? It's also going to give us kind of a good segue into talking about systems of linear equations, which is coming up in the next section. Okay. There we go. Okay, so we mentioned before that you can, because we're thinking of our matrix transformations as functions, one of the things you can talk about with a function is you can talk about the range of a function, right? You can talk about all the possible outputs that a function produces. So, as you consider every possible value for this vector x in Rn, what are all the vectors of the form a times x that you can produce, right? So in other words, which vectors y in Rm, in the codomain, which vectors y can be written as t of x for some vector x, right? What are all the possible outputs, right? So you might want to know, can you solve this equation? And this equation here, this turns out to be a system, right? This is a system of linear equations. And so practically the question of whether or not you can actually solve this thing is a question about solving systems of equations, and we need to develop some machinery for doing that. The uniqueness question, well, the uniqueness is also going to pop out when we look at solving the system of linear equations. But it turns out that uniqueness is related to finding vectors that get sent to 0. Okay. Now, well, let's just think about this in this example. Okay, t of x equals a times x. We were wondering, okay, what does the output look like? What does the range look like? Okay, so we write x is equal to xy, right? And we look at a times x. So a times x is going to be 2, 4, minus 1, minus 2 times xy. Okay, so I'm going to get, let me do it this way, x times 2, 4, plus y times minus 1, minus 2. Okay, but one of the things I can do here is I'm going to do, so this is 2x times 1, 2. I'm going to pull out, there's a common multiple of 2 there, and I'm going to pull out a minus sign from the other one. 1, 2. So I get 2x minus y times this vector 1, 2, right? And so what this tells me is that the only way that y can equal a times x the only way that's actually possible is if y is some scalar multiple of this vector 1, 2, right? So y has to belong to the span of the single vector 1, 2, so the solutions all lie along a single line, right? And that means that, any vector which is off of that line, not parallel to that line, you're not going to be able to solve. So the answer to whether or not you can solve is, well, no. The other thing you will notice is that this solution is not unique, right? Once I give you a y, there's actually many possible solutions. And the reason there are many possible solutions is that if I do a times the vector 1, 2, okay, what do I get? 2 times 1 minus 2 times 2, I get 0. 4 times 1 minus 2 times 2, so I get 0, right? So interestingly enough, 1, 2 plugged back into A gives you 0. So somehow this vector 1, 2. Now this is purely coincidence in this case. Normally this doesn't necessarily happen. It's interesting that it happens here. That this vector, which plays a key role for the outputs, is also relevant to the inputs. Usually these are different vectors, but this time they come out to be the same. So that's true. So if I call this guy, let me call this thing x sub 0. Okay. So because I have that, what that tells me is if I had, any other x, I could add on a scalar multiple of this x sub 0, and I know that that would be equal to a times x plus t times ax 0. But this guy is just the 0 vector, so I get a times x, right? So if I have one solution, if I have one value of x that works over here to solve for my y, I actually have infinitely many solutions because I can augment that particular vector x with any scalar multiple of this vector 1, 2. So I get an infinite number of solutions. Okay, now the key thing to note here is that the values of y where I can solve are the ones which happen to be scalar multiples of this vector 1, 2, and that vector 1, 2 generated both of the columns, right? The first column was 2 times that vector, the second column was minus 1 times that vector. This vector 1, 2 is sort of a basis for the set of all linear combinations that you can form from the columns of A, right? It's a basis for the span of the two columns. So this has a name, okay? So the column space of A is denoted by col A, and it's simply the span of the columns using this notation up here, column 1 down to column n, right? So the column space is just all the possible linear combinations you can form from the columns. And so what we kind of understood through our example, and it turns out this is true in general, is that the column space of A is equal to the range of T, where T of x equals A times x. So in other words, this equation y equals A times x can be solved for x if and only if y is in the span of the columns, if y belongs to the column space. Okay, right? And we can see that up here, right? Anything which is in the range, anything which is a multiple of A, so if y is equal to A times x, then it's automatically in the column space because A times x can always be written as a linear combination of the columns. And then conversely, if I was given a y and I knew that that I could write it as a linear combination of those columns, I could figure out what the coefficients are and use those to form my vector x. Okay, so that's how the column space is. It's just all the vectors that you can form by taking linear combinations of the columns of your matrix, and that turns out to be exactly the range of the corresponding linear transformation. Okay, all right. So a couple more examples. In the case of this guy here, we notice that the column space of A, well, it's going to be the span of the vectors 1, 2, minus 1, 1. And those are two independent vectors. They're not parallel, or sorry, they're not parallel to each other. Neither one of them is 0. And that means that you can actually get every vector in R2 using these two vectors. Figuring out what they are, that takes a little bit of work, right? So if I had x, y is equal to a times 1, 2 plus b times minus 1, 1. Well, then I could try to solve for a and b in terms of x and y. A minus b would have to be x. 2a plus b would have to be equal to y. And I could do it. 3a would give me x plus y, so a would be equal to x plus y over 3. B then would be equal to it would be equal to what? Y minus 2a. So it would be equal to minus 2x plus y over 3. I think that works. Let me check. I did that a little bit fast. If I do x plus y over 3 and I subtract that, yes, that works out. Okay, right. So you can always solve this, right? And not only can you always solve it, you can actually solve it uniquely, right? That's the only possible solution that's going to work in this case, right? So the span of these two columns is all of R2 because whatever vector, whatever x and y happens to be, right? I can find a and b, so every single vector is in the span. For b, on the other hand, I notice that. I know that 3 minus 3 is 3 times 1 minus 1. So the column space for B, well, by definition, it's the span of both vectors, 1 minus 1, 3 minus 3. But the second vector is redundant, so we don't need to include it. Anything that can be written in terms of both vectors can be written in terms of the first vector alone, right? And so, in this case, we simply get we get a line, right? We get a line. In this case, it would be the line, I guess, y equals minus x, right, through the origin, if we wanted to describe that column space geometrically. Okay. The other thing that you can associate to a matrix is the null space. By the way, before we jump to the null space, let me point out that the column space is it's a subspace of Rm. Why is it a subspace of Rm? Well, it's a span of column vectors, m by 1 column vectors, is a span of vectors in Rm, so we know that the span of any set of vectors is always a subspace. The null space turns out to also be a subspace. The null space is going to be a subspace of Rn. Okay? And the null space consists of all vectors that get sent to 0. Okay? Why is it a subspace? Well, notice that if x and y belong to the null space, and what does that mean? That means that a times x equals 0, a times y equals 0, then a times x plus y is ax plus ay is 0 plus 0, which is 0. And so that tells me that x plus y is in the null space. And similarly, we know that c times x is in the null space whenever x is in the null space. Okay? So the null space is closed under both addition and scalar multiplication. Of course, it's non-empty because the 0 vector is in there. The 0 vector is always in the null space because a times 0 is always 0. Right? So the null space passes the subspace test. So the other thing to note, and we kind of mentioned it already in our example, is that if I have some vector say x sub 0, and it's in the null space, then for any other x in Rn, a times x plus t times x0 is ax plus t times ax sub 0, which is ax plus 0, which is a times x, right? And so that means that there are going to be infinitely many vectors that all get sent to the same y value. So if this is y, right, this is y over here as well, right? And so that's going to play a role if you're interested in solving systems of this form y equals a times x when there's something non-trivial in that null space. Of course, if x naught is the zero vector, then adding t times x naught doesn't do anything. But if if this x sub 0 is non-zero, then suddenly there are lots of different vectors that all get sent to the same value. Okay. So in our examples, let's look at the same two matrices we had before. If I looked at the null space for A, okay, so think about having A times any vector x, so xy equal to 0, 0. What does that tell me? Well, that tells me that x minus y equals 0 and 2x plus y equals 0. And so this one says that x equals y, and if we plug x equals y into here, then this says 3x equals 0. And well, if 3x equals 0, then x equals 0 and x equals y, so y is also equal to 0. So, so in this case, x equals 0 and y equals 0, and that tells me that the null space for A, the only thing that's in there is the 0 vector. However, if we look at the matrix B, if we multiply by this guy, 3 minus 1, I'm going to get 3 minus 3. I'm going to get minus 3 plus 3. I get 0, 0. So this vector 3 minus 1 belongs to the null space of B. And in fact, you can play around with this and you can see the null space of B, it's actually everything that's in the null space is a scalar multiple of this vector. Although, being 100% sure that that's the only vector in, that single vector generates the entire null space, we maybe need a few more techniques to understand why that's the case. Although one way to think about it is that if that null space was the span of two non-parallel vectors, well, we know that two non-parallel vectors in R2 should span everything, and clearly not every vector in R2 gets sent to 0. The only way everything in R2 would get sent to 0 is if B was the 0 matrix, right? There are lots of values that we could plug in that don't get us to 0. So we expect that the null space is one-dimensional in this case. Okay, that's it for matrix transformations.